So when you act to the door, for example, you can push it or you can pull it. So you have to act a force. So you can imagine the action of a force. Okay. So the force is a vector quantity because it has the direction, not only the magnitude, but have the direction. Because, for example, you have the object here. It acts to this direction or this direction if you can feel different, right? Can act to this direction, this. So, of course, the force is have not only magnitude, a big force or not, or small, but also the direction. So remember that force is a vector quantity. Okay. So it not only magnitude, but also the direction. So the new unit of force is Newton. So for example, you can say I can force 2 Newton, 3 Newton. Okay, so it's a unit. And in general, if you have a body here, it can be acted by many types of force. For example, this one, it has a gravitational force. It has you can act the force in this case. It can have some friction here. Okay, so many force acting at the same times in one body. Not only one force, but many force. And also you have a string here, move to this. So you have the tension here acting to the body. Okay, that is a general idea for the force. So when you act by many force like this, so we have the resultant external force. So external force means it's a force outside the body itself acting on it. For example, you have this the force here, gravitational force here. Yeah. So the resultant means you make the sum. Resultant force, you make the sum of all the force, F1, F2, Fn, sum over all external force acting on the body. It's called, the name is resultant external force. And then in case all this force is balanced, they are balanced if the resultant force is 0. Balance means you make the vector sum. Remember, you make the vector sum, and if it becomes 0, then the resultant force is 0, and then all the force is balanced. For example, I have the case, if I have a object resting on the table, there will be 2 forces acting on the body, is gravitational force and the normal force of the table on it. So later I will explain you what does it mean of this normal force. But in this case, there are 2 forces acting on the body, and you have N, P is 0. So it means that you say N and P are balanced. Okay. And then the first law of Newton said that if the motion of the body is not disturbed by external influence is a force, then body moves with a constant velocity. So if it's acting by these 2 forces and they are balanced, or the external force is 0, right? No any. So the resultant force is, or the total force acting on the body is 0. So in this case, the object will move with a constant velocity. Constant velocity means if initially it's at rest, so it's still at rest forever. And if it's moving with some velocity, so the velocity will remain constant. So this we already know from the previous chapter, that if the velocity are constant during the motion, then if we have the displacement is a straight line. So in this case, it's a vector form, but if you project on 3 directions, as I explained from last one, for example, you have x at the time t equal to x0 plus v0 along OX and t. Okay, so the graph of x versus t, x0 for example here is a straight line. This equation is a straight line because it's a linear function of time. So the graph is a straight line. Okay, the power of t is here is 1, and x0 and v0 is a constant. It's known constant, and the variable is time here is, so the displacement depend on time as a linear function. Okay, so here is the motion with the constant velocity we know from the previous chapter. And then in case, object continue move in the straight line with a constant speed, okay, and then if it's 0, it's remain at rest. If is this one is 0, then it's remain at rest. So x all the way x0, so remain at rest. V0 equal to 0. So in this case, V0 is not 0. Okay, you have straight line. Also the straight line, but just this straight line with a 0 velocity, it doesn't move, it's at rest. So the line here is the parallel to the horizontal line, it's a t, to keep the displacement unchanged during the motion. Okay, that is the first law of Newton. So you remember the first law of Newton, it looks simple, but it's very, very important. So it's important in this sense. So the first law of Newton, we help you to define the frame is called inertial frame. Inertial frame is a frame to satisfy the first law of Newton. So to satisfy the first law of Newton means if, in this case, if the body is at rest, because in this case, the force is balanced. This force balanced to proportional, they are balanced, and the resultant force 0. Okay, so the first law of Newton is said that, okay, if the frame of the floor is inertial, if is at rest, it will keep at rest forever. Okay, if not, the force already balanced, but initially is at rest, but after, for some reasons, it is moving. So it changes the velocity. So in this case, not the law of Newton not correct, but in this case, the frame of the floor is not inertial anymore. For example, if you can imagine, you have a table. So this object is resting on the table, and then as we explained, there are two forces and they are balanced, N and P, and then it's resting on the table. Okay, so you said that, all right, so no external force acting on it, and then if velocity 0, the body simply remain at rest forever. Okay, so you say that the frame of the table here is a inertia. Now, if I act a force on the table, not on the object, okay, I act a force, I push the table. So imagine that you have a ball, not the object. It's a ball, very easy to get a move if you have, I think, something. You have a ball here. In this case, if you have a ball, and now I make a push on the table. I don't act on this object. I just act on the table. Okay, so this means that the force acting on the ball still the same. They are balanced. But in this case, you see, can you move? You push to the table and then the object is moving. You say it's move. It's move. Wow. Initially it's at rest. But then if you push the table quite very strongly push, and then you see the ball is moving, right? Have you ever seen? Agree? So in this case, you said, oh no, why? Still the force acting on the object still balanced, right? But initially at rest and then it moved, so it changed the velocity. Oh, is it the first law of Newton is not correct anymore? Right? No, still first law of Newton correct, but in this case, you can explain. Now, if you act the table and make the table moving, and the frame of the table is not inertial anymore. So in this case, if you see it initially at rest, but finally it's moved, so it means that this frame is not inertial. Not inertial frame. Okay? So the first law of Newton can help you to check whether the frame is inertial or not. It looks easy. If it's not inertial in this case, you don't act any force. No friction here. You delete the direct friction, just normal force. And if it's at rest forever is inertial. But at rest, initially at rest, but in some instant, it's moving. So at the time of it's moving, then the frame is not inertial. Is it clear?
Yes.
So remember that the laws of Newton only correct in the inertial frame. Tell me, who can ask me a question? So you agree with me or you want to ask me the question?
No questions.
Okay, thank you. Okay, so it clears, then we move to the next part. So we finish the first law of Newton. So we move to the second slide. How about in the case is the force are unbalanced? Okay. We already consider the balanced force. Balanced force means the object will move with a constant velocity. Agree? So I balance force, then V constant, then you have acceleration is no changing in the velocity means you don't have acceleration. So in the case, another case is unbalanced. Of course, we can guess. Now the velocity not constant anymore. Okay, so the resultant force is not zero, of course. Resultant force is not zero. And then in this case, V not constant. And also make the acceleration is not 0. Okay, and then if we, what does it mean of this? There are 4 cases. First one, if we make the object, stationary object, to move, stationary initially is stationary, is at rest and is moved, right? So you have a ball on the grass, and then if you push by foot, push it, and then it's moved. Okay, so unbalanced force can cause a stationary object to move. Secondly, speed of the object increase, so it's moving, but if act the force, it makes velocity increase. Okay, the third case, if you are going with a constant velocity and then you want to stop, then in this case you need some force to make the object to decrease the velocity, so to make the speed of the object decrease. And the fourth case, if the speed doesn't change, but only direction of motion changes. So can someone else give me one example for this case? And then in this case, for example, remember, speed doesn't change. So it means that the absolute value, magnitude of the velocity is constant, but direction changes. So when you say the velocity is not constant, including, because velocity is a vector quantity, it contains also magnitude and direction. If magnitude doesn't change, but direction change, so it makes the vector velocity change. Okay, so in this case, for example, in this case, but the direction changes. Can someone give me example for this guy? Nguyễn Đăng Sơn.
In the case of the moving things that collide with the surface like a wall, so its speed doesn't change at that colliding time, but the direction of the motion change. Like when it's dropped from the upside down, when it hit the ground, then the direction of the motion change with the speed.
Very good. Good. So Sean said that you have a wall. Okay. So you hit a ball to moving to hit the wall. Okay. And then it's collide with the wall, and after that it's move. So when it's coming, it go moving with the velocity v, and when it get out, it's a minus v. So in this case, during this collision, it is act by some force, right? Making it change the direction of the velocity. And in this case, velocity keeps the same magnitude and the direction changes 180 degrees. So in this case, you have elastic collisions. We will learn later. Okay. Can someone else give me another example? Anyone else give me another example? Nguyễn Đăng Sơn, can you read for me the BI ID?
It's BI12386.
3.
Yeah, 386.
86. Okay. Nguyễn Huỳnh Đức already have the mark. I want Phạm Gia Đức. Phạm Gia Đức. Let me check. Yes, Phạm Gia Đức.
So I think this another example is when we drop a ball.
What?
when you drop a ball in the vacuum.
Drop in the vacuum,
Yes. Is it true?
but the drop in the vacuum, the speed changing, right? Increasing. I'm asking the case during the motion, the magnitude of the velocity doesn't change, but only the direction changes.
Oh, okay. Okay.
Okay.
We have the Earth orbiting around the sun.
Ngô Hoàng Quân.
Yeah. So when the Earth rotates around the sun, its speed doesn't change, but the but the direction change.
Very good. Ngô Trần Hoàng Quân. You are not yet on the list, so I write your name. Ngô Trần Hoàng Quân, right? Hoàng Quân. Read me BI 12 and something.
362.
3, 6, 2.
Yes.
Good. So what Quân has that mentioned is circular motion, right? So if you have the circular motion, around a circle, and even the magnitude of velocity, like he said, if the Earth is moving around the sun, with the speed doesn't change, and every year you have the same period. Every year is repeat. It's the same period because the velocity with respect to the sun doesn't change. It makes the same period always, and then is moving around the Earth here and the sun here. And in this case, you have the circular motion. The velocity is perpendicular to the trajectory. So it's the velocity, and magnitude of the velocity doesn't change. So the velocity here still v, but the direction change. Velocity is this direction, in this direction. Change all the way, changing the velocity, with the direction, but magnitude doesn't change. And in this case, you still have acceleration. Okay. So in this case, the v is constant, but you have acceleration because of the changing in the direction. And then in this case, for example, you have from point A to point B, this velocity from A to B here. This vector minus this vector, you get this vector. So in this case, you have the acceleration is a centripetal acceleration. Okay. Good. Any question? Otherwise,
You have another example for the fourth situation where the direction where the direction changes but not the velocity, other than the planet Earth orbiting the sun and other than when the ball impacts the surface. Do you have another example?
yes. That is the circular motion in general with a constant constant speed. Okay. So you want to make
do you have another example?
You want to hear more example, or you want to give more example?
Do you have another example for us?
You are asking me, right?
Yes. Other than these two.
I don't have, but if you have, please let me know.
No, I'm just asking this to add more to my notes. Thank you.
Yeah. Okay, so I think maybe you can find another example, but very common one is this circular motion with a constant speed. So you can emit very naturally that the magnitude of velocity doesn't change during the motion, but the direction change all the time, making you still have the acceleration in this case. Then the acceleration in this case is called the centripetal acceleration. Okay.
Okay, thank you.
One typical example. And still, of course, you have some specific situation in the reality, but of course, that depends. Okay, thank you very much. So in that case, we move to the Newton's second law of motion. So we define, to go to the second law of Newton, we define the momentums of the particles. So a particle is moving. So you still hear me very well, right?
Yes, very well.
Oh, okay, thank you. Because
Yes.
someone disconnected for a while. Okay. Right, so give absent, no problem. Very good. So an object is moving. So we have the grounds. Then the object is moving with some velocity, and it contains the mass. So we define the quantity called momentum. So momentum is a vector. You know, it's P, vector P, equal to the product of mass and the velocity. Okay? So the momentums containing not only information for the direction of motion and the speed, but also the mass. And it become important because you can imagine that the object is moving, but the heavy objects and the light objects moving makes some different effect. For example, you can imagine that there is a body here, and then there's another body, big M, hit this object. So it's like a force. So if this guy is heavy, you can imagine, oh no, for example, I'm here and then there's very big guy hit me. Oh, it feels very bad, right? But there's a child, very small child, beat me, hit, you feel nothing happened. Even the child makes very, very strong motion of his hand, okay? But still I feel nothing. But it's a very big guy, very fat guy, is a heavy guy, make even small. Or even we can make, you can see on the road there are some accident. And then if is acting by a very big car or it's a van, it's a dangerous accident because this guy is too big. So momentums, we contain information not only the changing of the velocity, but also having the mass. So that is why we need a new quantity to get more information. So velocity is not enough, but you need also the mass. The mass also play an important role in this case for the force. Okay, so that is why momentums is the product of mass and the velocity, and also it has a direction. And remember that the direction of the momentum is the same as direction of the velocity. And now Newton, the second law of Newton, is contain the momentums. So when this guy hit, the big one hit the small one. So initially the small one is moving with the velocity v, and this one hit it, and the velocity changed to u. After pushing more force, it changed the velocity, making the change velocity by acting some force, of course, right? by acting some force, it makes this object changing the velocity from v to u. And the time taken when you change this velocity, or the times of the force acting on the body of this guy, acting on this guy, is delta t. Okay. So if you change the velocity, and then because you have the change, velocity have the connection with the momentum. Velocity change, you have momentum change. And Newton said that during this time, you move the velocity, the momentum mv to mu. So the changing in the momentums equal to final momentum minus initial momentum. Okay? Then the P. And a quantity determines to the you change how much you change the momentums. So you can measure the how much you change with respect to time. Change quickly or change slowly. Okay? And then this guy, you define is the force. So the force F here, making the momentum changing from this to this, and is determined by the formula is delta P, delta T. And when delta T very, very small, you have the instantaneous value. And then if you take the F is the limit of delta P over delta T, when delta T very, very small go to 0. So this one is a derivative. Is a derivative, and I denote dP over dt. So dP dt means it's a changing in the velocity with respect to times when the times very small. Exactly the same way we do with the definition of the instantaneous acceleration. Okay? And you said that the force will be proportional to the changing of the momentums with respect to time. Or you can say that under influence of this force, the momentum of the object changes from this value to this value. Okay? So you get the relation. If you have a force, you will have the changing in the momentums. And now, if mass is constant, so we have this dmv by dt is equal to the force. If mass is constant, constant mean mass doesn't depend on time, so you can get out. So we have m dv by dt. And you know that dv by dt is changing in the velocity is the acceleration. So we have another type. The form of the second law of Newton is F equal to ma. And this one is known from high school. You know already. You know this from high school. F equal to product of mass and acceleration of the object. But you know that this is the initial form of the second law of Newton. He stated for the momentums. And this case is more general than this case. This case only correct if the mass of the object doesn't change. But in case the mass of the object changing, you should use this formula. Okay? All right. Sorry, I need the charge for my computer. Is with sorry, I have a minute. I take the charge from my computer. So we have the form for the second law of Newton. We move to the next one. Okay. Second law of Newton said that the rate of change of the momentums, okay? Changing of the momentum with respect to times is rate of change, okay? dp, this one is dp by dt, okay? For example, I don't take the direction. If you have direction here, you have also direction here. But for example, you consider the magnitude to be easy to say. So then, rate change of the momentums of the objects is directly proportional to the applied force, and it occurs along the direction of the force. Along the direction of the force means, what does it mean? It occurs along the direction of the force. For example, you have initially velocity mv here, and after that, the changing after sometimes is a mu, right? So delta p is mu minus mv. So mu minus mv. So we have this one, and then you have this one. This direction is delta p. And delta p having the same direction as the force. So the force also pointing along this direction. So that is the force occur along the changing of the momentum occur along the direction of the force. So if you are acting is a straight line, you don't see it clearly, but you use circular motion, for example. Okay. So in this case, you have the velocity here and velocity here. If you make the changing, it has this direction. So this one is the direction of the delta p and also the direction of the force. And this force is called the centripetal force. So the centripetal force having the direction of the radius of the circle, and it's direct to the center of the circle. It's called centripetal force. Okay. So in this case, so remember that delta p and the force having the same direction. And if you base on this direction, you know, and then you know the direction of the changing of momentum, and vice versa. And another quantity we call the name is, if you take here, from here, you take the integral from 1, 2. So the initial place here, 1 and 2. So after place 1, you have the velocity. I make a little bit different here. So 1 here. and 2 here. So you move from 1 to 2, all right? So I make opposite direction to this, okay? Anyway, I change it a little bit to be consistent with what I'm doing here. It's not important, but okay, to be consistent. U, V, U, V, okay? MU minus MV. For example, V is 1, U is 2. 1, 2. If you make integral both sides, and then you get this integral equal to delta P. And then we denote integral of F dt. So the acting of the force during this time, it called the name is impulse of the force. Impulse of the force. Impulse of the force is a change in the momentum. Okay. So you, the question asks you, what is the impulse of the force? You make the integral of the force, which is for time during the period from T1 and to T2. And the meaning of this is a change in the momentum. So this guy is a delta P. Okay. If F is constant, you have the integral F. If F is constant, mean F doesn't depend on times. So you can get out the integral and you see F dt T1, T2, and this one is equal to F T2 minus T1 equal to F delta T. So if F is constant, so the impulse of the force is the product of the force and the time duration that it acts. Okay. In the case, if F depending on time, what happened? So you have the graph F depend on time. For example, F now changing with time. If F is constant with time means you have this line. F is constant, you have this line. And then you go from T1 to T2, you take the F, then the T, then the T. F, then the T, you see it is the area of this part, okay? And how about the case when F depending on time, changing with time, you have the curve like this. So in this case, integral of this is also the area of this, of the part least meet by this line to the horizontal axis. Okay, that is the area below FT graph between T1 and T2. Okay, for example, T1 here, T2 here. That is the impulse of the force. Okay. Right? To apply this, we make example exercise. You have a work exercise. So send me privately the results by message. Okay? So I see many questions, which is good answer, but different units. All right, so Nguyễn Phan Gia Bảo. Can you hear me? So firstly, I want to write your name. Nguyễn Phan Gia Bảo. BI12 048. Very good. Give me the answer. Very good. From 0 to 8. So it's the area of this. And area equal to one half the height multiplied by this one plus this one. Okay. So okay, so A AD plus BC. Okay, is the height is 1/2 10. This guy AD equal to 6 plus. Very good. What is the unit? Very good. So many people give me the good answer, but different units, wrong unit. So this unit is correct for the impulse. So the unit of impulse over force is Newton second. It's also not Joule. Okay, it's not Joule. Someone tell me this one is not Newton second. It's not Joule. It's not Newton. Very good. All right. Any questions? So this very simple question, and for us to imagine that is a force acting on the object is changing during the times A to B. It increase until here, and then it get the constant. And the impulse is during 8 seconds is the area of this one. Okay. So we are moving to the next example to apply the second law of Newton. So in this exercise, we apply the form of the law of Newton is F This is the second law of Newton. Okay. So because this one you don't have the number, the results as the number. So you write me the message is done. Okay. If you are done, you say done, so that I can know you are done this exercise. Đỗ Đức Khi nè. Yeah, I see many people give me answers. It's very nice answer. So I want to call David Đức.
Yes.
Sorry, little bit. I want to write the 7 BI 12.
0071.
Okay. 071. Right. So please go ahead.
So do I share my screen or?
Yeah, you
Okay.
you explain for the case.
Okay. So, okay.
All right.
So for case A, the bob moves to the left side because when it accelerates, the movement is when the train moves.
Accelerate means how about the direction of the
it accelerates
acceleration?
to the right. Let's say
To the right.
let's
Very
say
good.
it accelerates to the right. So the bob goes to the left because the bob
Okay.
is held on a line, so it more or less doesn't, let's say, isn't affected. Well, no, doesn't go with the train when it moves. So it moves to the left.
Move to the left.
Yes.
And then the explanation is because
It's on a line. So if it was, for example, glued to the surface, well, it won't move. But if it's on a line, well, it will move because it's more or less disconnected from the system. So it will, let's say, the change of the acceleration. Let's say the change of position isn't the same as the one of the train. So it's a little bit detached, as in. It's pretty hard to explain in English. I just don't know how to
Okay.
explain it, but it's observable. So
observable, right?
and I know the explanation, but it's hard to, let's say, re-explain how it works. I just know that because it's suspended on a line,
Yeah.
there's a difference in movement. So the train moves, but the ball doesn't move in the same time, like not at the same speed. So it's a little bit, the movement is retarded in a way. So that's why
Okay.
we see this this thing.
So you mean the bob here is connected by the string,
Yes, and so
and then this guy is a train. The train is here, right?
yes,
And when this point is moving, why this one still doesn't move? And
yes.
so it's somehow this one is moving, and then this still want to stay. So that is why it's later
But
than
it
this
still
guy. So
moves, but in a, let's say, the delayed way.
late way. It's a late
So
way.
that's why
there are some initial times, for example, delta t very small.
Yes.
And during this delta t, this guy move faster than this one.
Yep, that's it.
And making this. But after that,
After
the bob
that,
still
normally with gravity and everything, it should more or less go back to its position, but I'm not sure about that. But I know, no, actually no.
So
Actually,
I
no,
agree with you. Yeah, is it clear? I agree with you that during this time, very small at the times the train. So for example, train is stopping, okay, and then it's act by the acceleration during the time delta t.
Yep.
And then delta t very small. So then this guy go faster than this guy. This guy move, and this guy is some delay, right?
Yes.
It's not yet moved, and then it's still here, and this guy already. But after delta t, you understand?
Yes, logically it should go back to its position.
After delta t, after delta t, the train still keeping the acceleration. You understand?
Yeah. So yep.
The train still accelerate, not a go to zero. A is still constant. A and A is constant forever. Okay.
Yep.
So still after delta t, still the train have acceleration, and it is accelerate. But how about the bob?
If it continues to accelerate, normally the bob will still have a delay. But if it, for example, if it starts to accelerate, then it's constant. The ball will go back to its place. But if it continues, as you said, to accelerate constantly, the bob should always have not in the same position, but in a relatively similar position. Normally, I think. Not sure. I suppose that's how it is. It should stay in the same position if it continues to accelerate.
Okay, so I repeat your answer to be sure that I understand what you are saying. Okay, so you say that during delta t, so the position of the bob is like this. Yes. I agree. But then after this time, still the train is accelerate constantly.
Yep.
How about the position of the bob?
Well,
you say that change or not change? It
might change, but it will still stay on the left.
Stay on the left, but may change.
Possibly. If, for example, the acceleration goes to, for example, if it was at 100 kilometers per hour, and the at delta t, for example, at 1 second it goes from 100 to 200, then the ball will it will change even more to the left. The angle will go up.
Go up.
Yes.
So you mean?
Yep. And if the acceleration were to go down, the angle will diminish.
Okay.
But here
And
it's
then
only
it-
going up, so yes.
Yeah, and then your explanation, you have to explain by, I think you are feeling and like observing, right?
Yes.
From the experience, from the reality, you can. Okay, so I agree with this, but I agree with you at this, but I don't agree at this.
Yeah, because I'm not
Okay.
sure at all.
Yeah. Who give me?
Can I?
Nguyễn Huỳnh Đức. Okay, Nguyễn Huỳnh Đức, go. Sorry, because Nguyễn Huỳnh Đức already get the mark. Nguyễn Huỳnh Đức already get the mark. Very
It's
good.
okay.
Yeah.
From the case that David Duck answer, if after density the train have the acceleration, it's go the bob is.
Further.
I don't agree with this.
Yes.
I think
No.
that the bob is the same direction. Is turn to the
Okay.
F because
Still the same.
because
Very good.
acceleration is a constant. So F net is a constant, and then doesn't change in the
Exactly. Right. So we that apply the first law of Newton, right? If
Yeah.
F is constant, so then you cannot have the changing in the velocity, and then the situation is still the same. Do you agree, David?
Well, yes, but the thing is that I think you didn't understand what I said before. When I was talking about it, I said if the acceleration were to change, I said
No,
that like no, I gave an example, but before that I said that it won't change. So
Yeah.
I think that in reality the acceleration is not constant. So
yes,
the bob will move up.
Yeah.
it will
Right.
vary a little bit, but not a lot.
But in
Yeah.
this case, the frame is very idealism.
Yes, that's it.
Yeah. So I understand what David, because David observed from the reality. So
Yeah,
it's
reality.
good that because the train cannot get the constant acceleration at in a very short time, right? So it needs some time to to keep or to reach the constant G's value, right? But then, yeah, I understand. So still at the case, that is why I repeat my question is, assuming that we get the constant acceleration, and then the train continue accelerate constantly, okay? So what happened to the bob? And then you said that is like this.
Well, it was an example. I give an example.
Okay.
I said
okay.
it was if the acceleration were to change, like go from 100. If it
Yeah,
were to
of course,
example, yes,
of course.
I was giving the example, but I
Yeah.
didn't explain enough, so that's why it
Okay.
didn't go
Okay.
as
Okay. So now I understand. So what you mean here is acceleration is greater.
Yes,
Right?
if the acceleration were to go up,
Go up,
the
go
bob
up, and then you
would
get
go up.
more. You get more angle. Okay. Good. Okay. So I agree. So Huỳnh Đức, can you explain? So Huỳnh Đức said that if we keep constant, so the position of the bob still here. Okay. So Huỳnh Đức, can you give me the explanation why the bob is go to the left by applying the law of Newton, not by observing?
We have the two frame. The first frame, we have the two observator.
So the frame with the mark is on the ground.
Okay. So
the mark is on the ground. So here is the ground. Okay.
Yeah.
So here is a train, and the train is moving on the ground. So you have two frames. The frame is the ground.
And the frame is a train.
The frame is a train. I denote it number 2. Okay. Good.
In the train.
And then you choose the observer is standing on the ground or standing on the train.
Standing on the ground.
Okay. So observer is here. Observer is on the ground. Then
in the frame train, we have the train have the acceleration?
Yes. The train has acceleration in A means here is A, the acceleration of the train with respect to ground.
Yeah.
Very good. So acceleration of the train means acceleration train with respect to the ground. If you say in the language of the train. Okay. Next.
We call the ground is a 1. It's, maybe it's 2-1.
The bob is 1. Sorry, the ground is 3. I'm sorry. Ground is 3, train is 2, and the bob is 1. So the acceleration is 2, 3. Okay, sorry, that's my mistake. Okay.
And in the train.
In the train.
Because the example, someone in the train, we see that the train not move. Because
right. So okay, the train. I make the graph of the train with the blue color. So the train is here. The train is here.
Yeah.
This is inside the train.
And the observer is the train think that the train is not move.
Right. So this in the train. Train is this one. And then observer standing on the train, sitting on the train here.
Yeah.
Another observer on the train with a blue train. And inside the train, this observer see the object doesn't move. Okay, good. Then next.
And we call it the A212.
And A12. So the acceleration of the bob is 1, 2. Acceleration of the bob with respect to the train, 1, 2. Okay.
And we have A12 plus.
You mean this one 0?
Yeah.
Because observer cannot see the bob doesn't move.
Yeah.
Is 0. Okay.
And it's equal with A13.
If A13
3 plus
equal to
2 minus. Yeah.
and this one is 0. So this one equal to the acceleration of the train. So acceleration of the bob with respect to the observer on the ground is exactly the same as the acceleration of the train. Okay. And then if that case, why this guy go to the left?
I think some things have mistake here. It's not prove that A13.
If according to this, I would say the bob is still here.
Yeah.
Agree?
Yeah.
But David said that is go to the left. Can you explain why? Someone, anyone else? Other.
Wait, is it because we're looking from the perspective of the blue guy, so he doesn't like we don't see a difference, like we don't see that it's changing place, like from the drawing that you did.
The blue guy?
Well,
Yeah, this
yes.
after delta t, okay? The blue guy don't see the bob is moving, still at rest.
Yep.
But why in this case? It's a new position.
Can I?
Okay, Huỳnh Đức.
We have the blue guy and the bob is doesn't change position in the frame train. So the observer in the ground see that the blue guy and the Bob move.
Right. Yeah, agree. The blue guy move with this acceleration. They are moving
Yeah, yeah.
together. But
So-
why the Bob after go to the left here? Why it not stay here? It's still constant, right?
Excuse me.
Ngô Trần Hoàng. Ngô
It's,
Ngô Trần Hoàng Quân à?
yes.
Okay, Quân.
Can I ask?
You ask or you answer the question?
I want to ask a question first.
Okay.
Okay. Are we still at question A?
Yes.
Okay. So when the train accelerates to the right, the hanging point will move faster than the ball. So according to Newton's first law, when the ball is still moving, when a acceleration is applied on the ball, it will change direction. But the hanger is moving faster relative to the ball, so the ball is kind of moved backwards compared to the train.
I agree at this. So at this point, yeah, you have the same explanation as David said. Of course, we need some small times to bring the bob at the vertical at this position to the new position. Okay, this take delta t. And then the explanation as David said and you said is the same, and I agree. But my question is, after this time, still the train accelerate constantly and still the bob stay here at the same position. The train is accelerate constantly, okay? Still acceleration, but it's still here. Why?
Because gravity and magic.
Bởi vì đây là hệ kín ạ.
Hệ kín, isolate system. Okay? Which system is isolate?
The system with Bob.
The system Bob and
the train system, I guess. The two of them are isolated, they're not in the same system. Maybe.
Not really. Okay, so now I think I agree with Huỳnh Đức at this point. It's an explanation for the acceleration. So for example, we continue with the idea of Huỳnh Đức, okay? So now we consider the objects. We consider the bob. But I consider the bob in this observer with respect to the ground, okay? This guy, because the frame of the ground is the initial frame, and remember that the laws of Newton only correct in the inertial frame. So you consider the frame of this observer. And how many force acting on the bob? You have the gravitational force. You have the tension of the string.
There's
Okay.
also air resistance, no? But it's negligible.
We neglect the air resistance, okay? And also you see it doesn't move. It doesn't move on the train. Is on on the train is no acting with the air. You close the door and so on. And then on the train, this guy doesn't move, so it doesn't move, so it doesn't affect by the air resistance. That is another reason. Okay. On the train, you don't see it moving. It's just moving with respect to the ground and with the train. Okay, so you have P and the tension. And according to the second law of Newton, this is equal to MA of the bob with respect to the ground. So P and T is this one. This is the resistance force. This is a resistance force. And then you have F equal to M. A13 is equal to MA. Okay, so F is equal to MA, and this one is constant. So when this one is constant, mean the external net force doesn't move, and then this all the way vertically downward, and this one constant means T need to be constant, and T constant means you cannot change this angle. Okay, I remember who say this. I think Windick already said that. According to the law of Newton, when the external force is constant, then all the force acting on this constant and T is constant. T constant means if the string is lying like this, and it need to be make an angle because this one is not zero. A is not zero. A is not zero. You have this one. In the case here, you have P, you have T, and the resultant force. So the direction of acceleration is horizontal, right? And in this case, A is zero. A is zero, you have this case. But if this one not zero means you have to move. You have to move. And Y is left. It's left because in this case, you need the net external force. What? Having the same direction as the acceleration. Okay? In case you go to the left, you have F pointing the same direction as acceleration. Otherwise, for example, to the right, then net force is the opposite, is not correct anymore. This one correct means net external resistance force having the same direction as A. That is why it needs to go to the left. Do you agree with this explanation? Okay?
Yep.
Right. So now I give you another explanation. Another explanation, I choose blue one. So if my observer is standing here, okay? So from this equation, I still starting from this equation. So I don't break anything. I just from that equation, from T, I get M A13. But A13 is equal to sum of this. 1, 2 plus 2, 3. A23 is A12 is the acceleration of the ball with respect to this observer, right? So from here I have P plus T. I get this go to the left. M A23 equal to M A12. Do you agree with this equation? So I write here P plus T minus M A23 equal to M A12. if you look at the right hand side, ma12 is the mass and the acceleration of the bob with respect to the train. Okay, so if you consider that you are, or the observer is on the train, so then you can write the ma is like this. But how about on the left? So if you think about the second law of Newton saying that F total equal to ma, right? Second law of Newton is like this. So the right hand side, you already have ma in the frame of the train. How about on the left? So the left telling you the total force acting on the objects. So in this case, total force acting on the object is still gravitational force. Okay, the tension. Okay, easy to understand. But additional these two forces, it appears the new force. So this new force I call is the inertial force. So this is the normally force as you see in the inertial frame. So here I have the new force, inertial force, F inner, equal to m a12, and with F inner equal to minus m a23. So acceleration of the train equal to minus ma of the frame minus sign, remember. So what does it mean of this equation? This equation telling us that if the observer is on the train, then the force acting on the bob will be gravitational force, tension as usual. Additional this usual force, you need to add one more force. It's called inertial force. Appear due to the frame is accelerate. Okay, is it clear? So when the frame is accelerate, the new force appear. This one not zero in case this one is not zero. It's a, m a. Okay, a not zero. This force is not zero. If this one zero means the train is not accelerate, then you don't have this force appear. And then in this case, you say that the frame of the train is inertial with this straight to the ground. Otherwise, if it has acceleration, it is accelerate. And now the frame of the train is not inertial anymore. And in the frame is not inertial. In additional to the usual force you have, you need to add this new force. It's okay? Appear. Because the train is accelerate. Agree? So if use this equation and they are the same. And in this case, this of the blue guy, see the bob is at rest. So this one is zero. So we have T here, P here, and you have inertial force is in this. So that this one we cancel out the F, this one, making F inertial, F is balanced. And if they are balanced, mean the bob doesn't move with respect to the blue one. Okay? So on the frame of the blue guy, the bob is at rest. And then these three forces are balanced. So still, the first law of Newton is correct. If you add this force. If you don't add this force, it's not correct. If you don't add the force, P and T equal to zero is wrong. But if you add it, okay, good. Still, first law of Newton correct, because all the forces are balanced, and then this guy is at rest. At rest with respect to the blue guy. And then you see here, on the frame of the train, at rest because this force acting this direction, and because of this force, it make the bob moving from here to the left. It's okay. And this point Y is still here. This point is still here because this point is fixed to the train. So it's still under half the inertial force here, but inner here we balance to is kept by the train. Is balanced to the reaction of the train because it's fixed here. Okay, so they are cancelled out. But if it's free, if the bob is free, connect to the string like this, is moved to the left, so that these three forces are balanced. Is it clear? So it moves to the left because the force here go to the left is minus A. And similarly, to the case the train uniform velocity. So in this case, acceleration is 0. Acceleration is 0 is here. Okay, it don't move because you don't have the inertial force. Rotates uniformly. So A go to here, go this direction. If A go to this direction, inertial force we opposite to A because minus are here. So if this is the direction of the force, we act the bob to the right. Agree? So in this case, it's C. Because in this case now you have inertia in this direction. It makes the bob to go to the right. Okay? You agree with this explanation?
Yes.
Okay.
I guess.
All right, but anyway, what you feel is very nice, correct. So sorry, 1 second, I need to charge to my computer. On the motorbike, okay? And then initially the motorbike is at rest. And then if you accelerate, and then you're acting like this, because in this case, the inertial force opposite to the direction of the acceleration is go act you to the back. So that is why you feel there someone hit you, push you to the back, because that guy is the inertial force, because this inertial force opposite direction to the direction of the acceleration of the frame of the blue one of the train. Okay, so you can explain using the formula or applying the second law of Newton like this. If you agree at this point, we move to the next part. So we go to the third law of Newton. So the third law of Newton saying that, so you have two objects, A and B. They are hit, collide. So then when they are hitting, there will be a force exerted on A by B. So B we hit a force F A B. Vice versa. B A will act to be F B A. F B caused by A and F A caused by B. Okay, and these two force, this force putting at A and this force putting at B, and these two force having the same magnitude. So FAB is the same as BA. Magnitude is the same, but opposite direction. Opposite direction. Okay. So the meaning of this, this law of Newton is very important because it's telling you that no cells generate force. So if you generate a force, it's not appear alone. For example, if you hit the ball will act you back your hand the same force but opposite direction. They always appear together. It's a couple of the force. Okay. So that is why if you hit, you feel painful on your hand. Still, this guy feel pain. So because they are the same force. And if you consider this A and B as a system, isolated system, closed system or isolated system, A and B, a system, then the force, the interaction between A and B with this force is called internal force. Okay, the force inside the system, that is the internal force, to be distinguished with the external force. Okay, so for the third law of Newton is simple. Understand like this? Now I will introduce some everyday force. So the force we meet every day is, you have the gravitational force. I denote is Fg is mg. So is we meet from the previous lectures. So this force is I already explained. I already explained this case. That is, you have the Earth. The Earth is here. The center of the Earth is here. So for the objects moving on the close to the surface of the Earth, is we attractive force between the mass here and the mass concentrated at the center of the Earth. So this guy is mg. Gravitational force is the attractive force. Okay. Any object on the ground of the Earth, it will be attracted by this force. You cannot avoid it. You always. The second type of force is a normal force or normal reaction. What is it? So, for example, you have a table. This is a table. Okay. So the object is resting on the table. So the normal force is, because this force we act by the mg, gravitational force. So under this force, if we act to the surface of the table, the table here. So here is the surface of the table. So this guy, we act to a table of force. I denote is W. And under this force, we remember the third law of Newton, right? If the object act to the table of force, then the table will act back a force with the opposite direction and the same magnitude. That is called, to put on the object, reaction. It's called the normal force. So the normal force is the force of the surface of the table acting on the objects. If you don't have the table here, so the object will fall down. But if you have the table here, it acts a force here, making this two force balance.
and then the object is stay at rest and it's equilibrium. It's in equilibrium. It's don't move. But you don't have the table. Put out the table is the rope. So the table already supported by acting a normal force on it to keep it balanced to the gravitational force. And then this guy will be at rest. And then in this case, you have P and N equal to 0. If you neglect the friction, so this guy 0 means the object will be at rest and in equilibrium. Okay, and why the name is normal? This force having the direction perpendicular to the surface. Perpendicular to the surface. Okay, that is why the name is normal. Normal is the perpendicular to the surface. So if your surface is not like this, but your surface is a curve, so what is the direction of the normal force? So in this case, the surface having the direction is a tangent to the curve, and the normal force is like this. Radius direction. How about this? If the body is here, the surface here, so the normal force is like this. All the way perpendicular to the direction of the surface, or is a radius like this. That is why the name is normal. Okay, so the second type of force is a normal force. Normal force is a reaction of the surface on the object because the object is push a force on the surface. You feel the heavy, you feel the weight, and the force that the object acts to the surface is W. It's called the weight. It's the weight, and the weight and the normal force obeying the couple according to the third law of Newton from the same magnitude, opposite direction. So the magnitude is the same, but opposite direction. You see, opposite direction. And the weight is putting on the table, and the normal force putting on the objects, different objects. Okay, this put here, this put here, and they are not. Be careful. The weight here is not act to the object, but act to the table. If you consider only object, there are only these two forces. No W. Okay, remember, no W here. W is the force acting on the table, not the object. Don't be confused. So the weight. The weight is the force. They are the same. And in this case, you see that the N equal to the mg, and the normal force equal to weight. So the weight equal to mg. So in this case, the weight of the body here equal to mg. Okay. All right. So find the weight of objects resting on the table, but now my table is in this case. I put my table is here, like this. Incline to the horizontal. This is a table. With the mass m, the table is inclined to the horizontal an angle alpha. Find the weight of the objects in this case. If you remember, for the case, the table is horizontal like this. I already find the weight is mg, okay? How about this case? That is, who can? Classroom, link classroom. Hoàng Long, you are asking me the link classroom. What is it? I don't understand. Yes, right. Okay. Okay, Huỳnh Đức already finished, but do you have someone else? Okay, to be quick, Huỳnh Đức, can you present?
The answer is the weight of the object is mg.
Two other. Okay, sorry, Huỳnh Đức. Nguyễn Phú Huy.
Okay, so the weight of the object is mg.
Nguyễn Phú Huy, can you hear me? Huy?
Yes, I'm speaking.
Nguyễn Phú Huy.
Can you hear me?
Sorry. Sorry, I forgot to
Okay.
it's my headphone. Huy, can you repeat?
Yes, can you hear me?
Sorry, that's because Huy, can you tell me?
Yes, okay, so
Oh, sorry. Okay, tell me.
The weight of
Sorry, tell me first BI12 and something.
BI
196, right? Okay, go.
Okay, so the weight of the object is mg sine alpha.
Yeah, why?
Because the weight of the object is equal to normal force, and because the
it's
object
mg here, and the normal force is perpendicular to the surface. Okay.
Yes, and it's equal to mg sine alpha.
Yeah, and then you have mg plus n.
For example, this object is resting on the table with some friction.
Yes.
So friction we still not yet do, but okay. Anyway, I think equal to 0 is resting on the table. Okay. So if you consider on the vertical direction, you project this on a y, then you get, you project mg to a y is alpha is here, right? So you get minus mg cosine, sorry, alpha is here, sorry, alpha is here, cos alpha minus psi, because this is going down, plus n. Friction is perpendicular to OY, so it's 0. So it's 0. So from here, n equal to mg cos alpha, and the weight is equal to n, equal to mg. Very good. Okay. So go back home. You do this exercise. Okay.
Okay.
Yeah. And then friction we learn from the next one. And all right, so I don't know. Okay, wait me a minute, I need to take the screenshot. Okay. So we stop the class now, and we have the exercise tutor next week. All right.
Teacher,
so yeah.
can I ask you a question? Can you upload this lecture on Moodle? Because I think we need to revise it for the midterm test or the following test.
Yeah, okay, so actually, as I explained, I don't know, I explained for the Thursday class or L1 or L2, but this year I don't check the attendance list, so I don't want to move to push to give my lecture to the Moodle to encourage you to to attend the class, because I don't want to spend time with the check attendance list. And which whom already follow my lecture during this, I go very slowly, right? So I think you don't need the lecture note.
Okay, thank you.
Is it okay? Because equation formula is not so many, and then I go also slowly, and then I think you have time to write down what is important for yourself to take note. And also I want you to take note by yourself the important point. And with this exercise, you take the screenshot and you do. Okay?
Okay, thank you.
Yeah, thank you. Sorry. All right, so see you next time, and